Hi guys, so today we are going to be making a linear regression model, and what a linear regression model is to attempt to model the relationship between these variables like x and y by creating a linear equation. And it can also be used to predict like future values. And so I'm using Google Colab. And Google Colab is a notebook where you can write Python code, and all you need is a Gmail account. So feel free to follow along. But ideally you can use any application you want, like Jupyter Notebook, maybe even REPL. And so the first thing we need to do is import our libraries. All right. So first, I'm going to import NumPy because we learned NumPy in our last session. I'm going to continue using that. And we also need matplotlib, specifically the Python plot. And so we're going to refer to matplotlib.pyplot just as PLT to make it shorter on us. And we also, to create a linear regression, we're going to borrow this from another library called sklearn. And we're going to use the linear model, and we're going to import linear regression. Okay, and so the next thing we need is our data set, all right, or data. And so I just made up some data values right here, but usually you know what data you're going to use. So we're going to, basically we want to create two arrays. One array to hold all the x values, which is time, and the other array to hold all the y values, which is tree height. Okay, so to do that we can do x is equal to, and to create an array we just do np.array, and in here I'm just going to copy and paste these values in here, and you want to separate the values by commas. Just do that. This might take a while. Okay, and then we want to create an array for all our y values. Copy and paste. Okay, you can spend time formatting and making it nice, but it's just as long as it works, it's fine with me. Okay, so here we can actually plot the values if you want. So we do plt.plot, and we're plotting x and y, and we're making a scatter plot. And so first of all, if you plot it, it gives us the graph, but it's like a line, and I want it to be scattered, so I add another parameter. It's like it. See, now it's a scatter plot. Okay, so it looks like we have somewhat of a line, right? But we want to find out what the equation of the line really is. So this is where linear regression comes into play. So I'm going to create a variable and I'm just going to set it equal to linear regression so it's easier on us. Now if we try to fit the values with a line, let's try running all our cells, and it gives us the error. And basically the reason why is, so this X array is something that's called a 1D array. Basically we can see it, we can do X dot shape, and so basically it's just one column or one row and one column. But for linear regression, it's expecting a 2D array. And so 2D as in we want to combine this X array and the Y array together. Right? And so to do that, we can do something that's called, we can set the X variable to X dot reshape, and in here we're going to put -1, 1. So what this does is the 1 just means we're going to add another column right here, like right after this comma, and -1 means that the elements are going to remain as they are. Basically there's going to be like no shifting. So if we run this now, it shows us we have like 2 columns now, 2 shapes. Yeah, okay. So now if we do reg.it y, it works. It doesn't give us an error anymore. And so linear regression also predicts future values, right? So we can create a variable called y predictions, and we want to predict the y values, right, from like the x like that. Basically, like as time goes on or as x increases, we want to predict the correspondent y values, right? And so now we can plot the like points, and this time we can do plt.scatter, but you can also do it this way as well. I'm just gonna show you different ways how to graph it. And then we can plot x values, the predicted values, and we can also set the color. So we could do colors equal to, I don't know, blue. So you can see that it plot our line, and yay. So last thing we need to do is, let's say we want to find the equation of the line. where y is equal to mx plus b, and so m is our linear coefficient, right? So we get linear direct, that stands for coefficient, and b is our y-intercept. So this, and so you can print out the equation of a line by doing y is equal to, now remember m is a number, integer, and y is a string, so we want to format it. So one way to do that is we can do this plus brackets and then do dot format, and here we put m because m corresponds to the first bracket right here, and b is the second bracket right here. And so when we run it, it gives us the equation of the line.
Hello everyone. Today we're going to have our second session of data analysis on scientific research. Today we're going to do two demos on creating a histogram and creating a scatter plot respectively. So let's first start with creating a scatter plot. And the problem is to compare the silicon data with silicon dioxide data on the associations between their wavelength and index of refraction, which we use N to represent. And before let's start all the steps, let's first have a brief review on the things that we learned for the last session. So remember, the first step that we're going to take is called data pre-processing, in which we deal with missing data and the noisy data. Then, if we want to compare more than one data sources and figure out that their unit systems are not the same, then we're going to use the small steps called normalization in the data pre-processing. And after we finish data pre-processing, we're going to start importing our data. And I use these two Python lines to import my data. Remember the difference between them. The first line is to read the data digit by digit, and the second one is to read data by data. So we get 0 as the first data for the first Python lines, and we got 0.471 for the second Python lines. After we successfully import the data, we need to use list or array list to store our data, and eventually plotting our data requires some Python plotting lines, like those shown in this PPT. So I put two most common graphs that we use, the histogram and the scatter plot, which are also what we're going to plot today. And this process is called data visualization. And we'll start tackling these problems by starting with the first step, data pre-processing. So if opening our file, the silicon file, and also the silicon dioxide file, we can figure out that there are two problems between the data file. The first is that the number of data in a silicon file is more than that of the silicon dioxide file. And what we need to do is we need to first delete the data with the wavelength that is larger than 350 nanometers. Okay. And the second problem is that the data do not match with each other. We have 300 and 300 for the first data, but we have 310 and 302.4 for the second data, which do not match with each other. So what we're going to do is we're going to delete 302 to 308 to make sure that our second data match. And we're going to repeat this process for the following data, and we'll eventually gain a new data file for our silicon. So I have already done it. Silicon number 2 file. And let's see. So now we have a silicon file that matches with the silicon dioxide file with 6 data in total, and each data match with the other. 300, 300, 310, 310, 319, and 312. So there's a small discrepancy right here. We can just ignore the difference because it does not matter much. And after we're finishing dealing with our data pre-processing steps, let's open our Python IDE and start import our data. Oops. Oh, remember, before we import our data, there's another really important step that we should take. Remember, our task is to plot the graph, and we need to have something imported so that we can plot our graph. It is the matplotlib, right? Matplotlib.pylab SPLT. The reason we put SPLT here is because that the name for matplotlib.pylab is too long, and we do not want to repeat it again and again in our following Python lines. So we just use PLT as its abbreviation, and we can just refer to PLT whenever we want to use the matplotlib.pylab. So after we successfully import PLT, next step we're going to take is to import our data. And we do not have to remember the Python lines for importing the data because it's too long. The only thing we need to do is to know how to use them. And we can just simply copy and paste it from either the internet or your previous code. Here. But remember, we need to change our file name. Let's see. Our file name is C, Python, and silicon number 2. Okay, silicon number 2. And we also need to import our silicon dioxide data. So we need to have another copy and paste right here. But this time is silicon dioxide number 2. And we need to change the name for this from data to data 2 for silicon dioxide number 2, because we need to distinguish these two data sources. If you put the same name right here, it gets into trouble actually, because you cannot distinguish the two data sources, and you will eventually fail when you try to store data of these two different data sources. Okay, so we refer to data for the data of silicon, and we refer to data 2 for the data of silicon dioxide. And after we successfully import our data, next thing we're going to do is we're going to store the data of the two data files. And what we're going to use a for loop. So for I in range 1 length 1 comma length data. Remember, the reason why we need to put 1 here, it's actually, we don't need a reason actually, but it's just because that my data file, first line for my data file is these words, and we do not need to read these words into our IDE. So we start reading the data source from the second line. And remember, when we need to read second in our IDE, we need to minus 1. So 2 minus 1 equals 1, and we put 1 right here, meaning that we start from the second line. And remember to put a column after the for loop lines. Okay, and I forgot something actually. We need to first create the list to store the data. So first list that I'm going to create is called silicon wavelength, and the second is silicon index of refraction. We use N to represent our index of refraction, remember? And we also have those for silicon dioxide. Okay, so now we have our for list. Ready? We can start our for loop. We need to add each wavelength of silicon in our data file into silicon wavelength list. So we're going to use the append function of the list. Append data, and it's line I. However, it's here. It's the first column. The wavelength is the first column. So we need to put 0 here, representing the first column. And we're going to do the same thing for the index of refraction of silicon. Yeah, and it's the index of refraction is in the second column. So we put 1 right here. Okay, so we do the same for silicon dioxide. And remember, it's data 2 right here. And it's also the first column for wavelength. Data 2, line I and column 1. Column 2, I mean. Okay. It's also line I plus 1 here and column 2 right here. We always minus 1 for the IDE if we want to refer to some number. I mean some sequence. Okay. So after we successfully store the data right here, okay. Oh, there's another mistake that I made in this code. Sorry for that. Because it's length data right here. We cannot combine the data for, oh, actually we can, because we have the same lines numbers for both data sources. We have 6 lines here, and we have 6 lines here. So 6 lines for both data sources, so that's all right. If the lines are different from 2 data sources, you need to build another for loop for the second data source, remember. Okay. So after we successfully store our data, we need to plot them. And the lines we use is PLT, remember, PLT refers to matplotlib.pylab here. And we use scatter plot. Yeah. And yeah, for our first first set of scatter points, we use the silicon data. And for the x-axis, we put wavelength. Remember, the x-axis comes first. And then we put the index of refraction in the y-axis. The y-axis comes the second. And I want to use the color red for the silicon data. And the size of the scatter points, I want to use 1. So remember, these 4 things are all the parameters of plt.scatter: x, y, face color, and size. Okay, so remember, we have it here. These are all the parameters. And we choose x, y, face color, and oh, it does not have face color here. Oh, because we are using the pylab, and it's similar. Face color and also size. Okay. And we do the same thing for silicon dioxide. Wavelength as the x-axis, and index of refraction as the second axis. We'll use color green instead for silicon dioxide, and size is also 1. So let's see. Okay, let's run our code. Wait, So here, to select this one and run our code. Okay, so, the points is relatively small, so maybe we'll adjust our size of points to 10 and run again. Yeah, it's much better now. So we can see that our data are plotted correctly and perfectly on our scatter plot. And this is the result of our answers to our questions. So we can conclude some conclusions from our scatter plot right here. For example, the silicon dioxide. Yeah, the 6 points are actually above those 5 points for silicon. And we can make useful conclusions from this graph. Let's see. Yeah, so the next thing I want to mention is that, so if you simply put up this graph, then people may get confused with what the x-axis and the y-axis represent. So this time, you need to say, you can put some labels for your x-axis and y-axis. For example, I will put label wavelength here with nanometers as its unit. Oops. And I will put index of refraction for my y-axis label. Let's see. Okay, so now we have our x-axis label and y-axis label. Great. And this is the end of our first problems, like plotting a scatter plot to answer our questions. Now let's come to our second problem. The second problem is actually to plot a histogram, to create a frequency histogram for parameter P5 in photo data. So remember, the reason why we need a histogram is that we need to identify the frequency of data that falls in each class in a measurement scale. So for example, we may have 2 ones, 3 twos, and then now we have the frequency number 2 for the category 1, and we have the frequency number 3 for our category 2. Does that example make it clear? If it doesn't, don't worry. Let's start our demo to illustrate that. So now let's open our photon data file. If it's correct, yeah, it's correct. Okay. So now we have our photon data file. And, I forgot to put the format of it. But, yeah. Not actually remember, but let's see. It has pattern. So 3 as a group, 3 line as a group, 3 line as a group. And our parameter P5 that we need to figure out is in the very first data. It's the very first data of a group. So we have this data as the P5, the first P5, and this data as the second P5, and this one for the third P5. Sorry that I have just figured out that I forgot to share my screen for the rest of the recording in this afternoon, so I re-recorded the following part. After we distinguish what P5 are in the data file, the next step we're going to do is to write our Python lines. And remember, the first thing to do is to import our matplotlib.pylab as PLT, as usual, because we need to make sure that we can plot the graph, and we need to import our matplotlib first. Then we'll import our data file inside. Noticing that here I use the first Python lines for importing the data. Remember, the first one read the data, digit by digit, which is actually this one. So digit by digit, we first read 0, then we read the dot, and then 4, and then 7, and then 1. Okay. So this kind of Python lines, importing Python lines requires us to do something in the following so that we can guarantee the digits are combined together within a data. So we need to ensure that 0.417 is complete data and need to be separate from 0 and 0.942. So this is what this code works for. So let's open our data file. We can see that take minus 1.11788 as an example. We first read minus 1, then we read the dot and add the dot to minus 1, and then we continue to read 1 and then add the 1 to minus 1 dot, and then another 1 and 788. So in the end, we have a complete data. And while encountering with the space right here, the while lines will read this data index I dot space equals is true, and then the while loop will stop. So finally, we will only get minus 1.11788 for our first file here. And don't forget to transform the file from a string type to a float type so that we can plot it in a histogram. And after we have done all these steps of like adding the digit into a complete data and transforming the string type file to float type, we finally can store the file into p file list, which we created right here. So remember, we import our data first, then we create our list, then we store our data, and eventually we plot our histogram. And yeah, let's run our code. This is actually a histogram, but let's run again. Okay, so look at this third picture. This is the histogram that our code runs. And these are the parameters of plt.histogram, remember? So we have the thing we need to plot P5 and the beans. Remember, the beans are a collection of data in a specific range. Like these small rectangles here are beans. And since we have 100 rings, it means that we have 100 rectangles right here that compose the whole distribution. And his type here, the bar, means that we have these shaded regions. So the opposite of the bar is the step here. The opposite of bar is, here's pi and his type equals step. So if we adjust it to step, we'll only gain the line on top of the distribution. And we have our x label on the x-axis, p5 right here. And we also have our y label right here, the frequency. So that is all the solutions we have to answer this question. To create a frequency histogram for a parameter p file in photon data. And I hope the two demos today can work as a practice for you to prepare for maybe your future data analysis experience using Python in your research. And that's all. And thank you, everyone. Wish you a good weekend.